Hi, this is Gordon Parker from Michigan Tech, and in this video I'm going to cover the inverse Laplace transform. First, let's look at a brief motivation. Let's say that you're faced with a g of s, a Laplace domain function that looks like this. (7 over s plus 1, s plus 2). This stinker isn't in too many inverse Laplace transform tables, or I should say Laplace transform tables. But we can still take the inverse Laplace transform of it. And the way we do it is we can break this up into two pieces where each one of those pieces is in a Laplace transform table. S plus 1 over s plus 1 and 1 over s plus 2. Once we have it broken up into that form, then we can go 7 e to the negative t minus 7 e to the negative 2t. I'll go ahead and multiply that whole thing by a unit step function just to remind myself that as far as the Laplace transform is concerned, this function is annihilated for negative time. Okay, so done with the motivation. Now let's go on to a few definitions. Let's see. First off, the number of times that a root appears in a polynomial is called its multiplicity. That's going to be very important as we figure out how to break up functions into this form. Another definition is that if we have a root with, and actually maybe I'll just say that this is m. So a root with multiplicity, or m, equal to 1 is called simple. Great. A root, let's say a root with no imaginary part is called real. I think most people remember that. And on the other hand, a root with an imaginary part is called complex. Great, so now we have some definitions. So the number of times a root appears is its multiplicity. If the multiplicity is equal to 1, we call it simple. And if a root has an imaginary part, it's complex. Quick example. Let's say that we have a Laplace transformed, or a function in the Laplace domain that looks like this. Focusing on the denominator, because that's going to be important for us for the partial fraction expansion, we can say that we have a root at s equals 0. It has multiplicity 2. We have a root at negative 4 that is simple. And this is complex. We can see that because we can check it. If we look at the square root of this 2 squared, so that's 4, minus 4 times the coefficient here times the coefficient there, so that'd be minus 40. Since that is the square root of a negative number, we know that s squared plus 2s plus 10 has complex roots. And we could finish this off and calculate them. But in terms of classification, that's good enough. Okay, so now we can classify the roots of our denominator. Now let's go ahead and just outline the steps for the inverse Laplace transform. So if we want to take the inverse Laplace transform of some Laplace domain quantity capital G of S and get G of T, there's really just a few steps. The first step is to break up the function, like I showed in that motivation example. And you want to break it up into pieces that are in your Laplace transform table. Now, once you've done that, you can actually write out G of T. So maybe I'll add another step in here that just says write out G of T in terms of some unknown coefficients. That's kind of important because once you've done the breakup part, you're pretty close to being done. In other words, you can look at G of T and have a very good understanding of what that function looks like. You'll know that it has exponential terms or ramp terms or sinusoidal terms, etc. Tells you quite a bit about what that function is. The next thing is to take the inverse Laplace transform of the parts that you've broken up. And the next part is solving for the unknown coefficients. There you go. Okay, so let's just do a little example of just breaking up a complicated function. So let's say that we have some v of s is equal to s cubed plus 6s plus 14 in the numerator, and s squared, s plus 3 cubed, and s plus 7, and an s squared plus 2s plus 10. So instead of going into all the rules about how to break this up, I'm just going to do it by example. If we do a quick classification of the roots in the denominator, we can see that we have one here that has multiplicity 2, a multiplicity 3. Maybe I'll change this to a 4, just so we clearly see that it has multiplicity 3 because of that it's a cubed quantity. Here's a simple root, and here's our nice complex roots. So here's how this breaks up. This one breaks up into a c1 over s squared plus a c2 over s. My c's are these unknown coefficients. Let me switch to red and focus on this term now. This breaks up into c3 over s plus 3 cubed plus c4 over s plus 3 squared plus c5 over s plus 3. Switch to another color and focus on this term, our simple root. This gives us a c6 over s plus 7. And finally, one last color, one last root. This breaks up into two pieces. Here we'll get a c7 s plus 2 over s squared plus 2s plus 10 plus a c8 times 3 over that same denominator. Now, the real roots, breaking those up, is fairly straightforward. Hopefully you saw the pattern. Because this one had multiplicity 2, it broke up into two pieces. Because the s plus 3 had, or I guess I should have made that s plus 4. Since the s plus 4 had multiplicity 3, that broke up into three pieces. Our s plus 7 was simple, so we had 1. And our complex roots broke up into 2 with some rather strange looking things in the numerator, an s plus 2 and a 3. So let's look at why that is. it really has to do with the particular Laplace transform table that I'll be using in this video. And the way it goes is like this. The inverse Laplace transform of s plus a, oops, somehow I lost my, there we go, s plus a over s plus a squared plus b squared equals e to the negative at cosine bt. And the inverse Laplace transform of b over s plus a squared plus b squared equals e to the negative at sine bt. So the thing to take away from this is that whenever you have a complex root, like s squared plus 2s plus 10 will give, then you get two pieces in general. A decaying exponential, one with a cosine term and the other with a sine term. And this form of the denominator is what we call completed square. Something that you probably did a long time ago, maybe in high school. So we can take a polynomial like s squared plus 2s plus 10 and write it in this completed square form. And when we do that, we identify what a and b are, and that's why we have these strange terms up here. This is a and this is b for this particular polynomial. So let's look at that in just a little bit more detail. So in the previous page we had s squared plus 2s plus 10, and if we want to write that in completed square form, you can memorize the formula, or you can just know by working this out that this a needs to be 1/2 of that coefficient. So this is going to be s plus 1 squared. You can double check that because you square it out, you get an s squared plus 2s plus 1. So that works. I have that and I have that now. And so my b squared, in order to get this 1 up to 10, I need 9 or 3 squared. So my a was equal to 1 and my b was equal to 3. So that actually, if I go back up a page, shows that this should have been a 1, not a 2. Okay, so that was a mistake back there, but now we've got it fixed. And that tells us how to fill in that term and that term that corresponds to the s plus a and the b. Great. So now we know how to do step 1 of the inverse Laplace transform, and that is breaking up the function and how to deal with those pesky complex roots. Now, let's go ahead and do about half of an inverse Laplace transform. And I'll stay with green just because green's kind of a nice color. So let's say we have s plus 3 over s squared plus 14s plus 58. That's a nice one. So first we break it up. Focus on the denominator, and we would go, well, I know I'm going to have a c1 over s plus, I better look at this. First, let's check if it's complex. If I go b squared, that's 14 squared minus 4 times 58. And 4 times 58 is bigger than 14 squared, so that is complex. So I have to convert this into the completed square form, or s plus a squared plus b squared. My a is 7, which is 1/2 of the 14. So I have that. And that gives me s squared plus 14s plus 49. To get from 49 up to 58, I need another 9, and so this is a 3 squared. And that all works. So a is equal to 7, and b is equal to 3 again. Okay, so now I can finish breaking this up. Let me continue down here where I have a tad more room. C1 over S plus, I'll have an C2 S plus A over this denominator plus, I guess I ran out of room anyway, 3 times C3 over that denominator. Now, I said we're going to do about half of this. Here's the next part to finish this off. I can actually write out g of t, the inverse Laplace transform quantity. I look at this, C1 over S, that's a step, so I get C1. I look at this, and I guess I didn't write the A in there, maybe I should do that, but it really doesn't matter a whole lot. So I have a C2 and times the S plus A, so that gives me C2 e to the negative 7t cosine b of t. My b was equal to 3. Then I have this, so I'll have a plus C3 e to the negative 7t again, sine 3t. The whole thing times a step. And I have a great looking inverse Laplace transformed quantity. I can see that it has a step piece, so it jumps up. And then it has a decaying exponential piece with some wiggles in it due to the sine of t, or sine 3t cosine 3t. So I actually have a feel for what this response looks like. I don't exactly know what the combinations of all those terms are, but again, it gives me a pretty good feel of what we have. Now, we can actually kind of brute force the very last step for this example, and that is finding what C1 and C2 and C3 are. So let me scoot this up just a little bit, just so I can see these. So here's how we'll do that last step. Let's just say we'll kind of brute force it. What we'll do is we'll realize that C1 over S plus, I'm going to combine these up, C2 S plus 7 plus 3C3 over S squared plus 14S plus 58. That has to equal the g of S that we started with. So let me move up just a little bit. This g of S. Oops, something bad happened as I was trying to scroll up. This g of S. S plus 3 over that denominator. So I'll just write that here. Say that this has to equal S plus 3 over this denominator. Okay? So what I'm going to do is just move this up a little bit. Like, actually, I'll just scroll it all the way up. So what we have to do is figure out what C1, C2, and C3 are. And the way we can do it is take this expression and get it back into that denominator. So we'll take C1, multiply it by S squared plus 14S plus 58 plus this numerator times S. And I can write that denominator in there now. And this numerator has to equal that numerator for every value of S. So no matter what value of S I pick, no matter what complex number I stick into S, those two numerators have to match. And the only way that's going to happen is if every single coefficient in this polynomial of s matches every coefficient in that polynomial in s. So I need to multiply this thing out, this thing, and match up coefficients in the polynomials of this and this. Okay, so let's do it. It's a little bit painful, but gives us a nice answer. So let me do the s squared terms first. S squared. I pick up a c1 there and a c2 here. Now I'll do the s. I pick up a 14c1 here, and I pick up a 7c2 here, and a 3c3 here. And finally, I have a 58c1. And that numerator has to equal s plus 3. What this tells me, it gives me three equations really. It tells me that c1 plus c2, the coefficient of s squared, has to equal 0. There is no coefficient of s squared on the right. And this has to equal 1, that coefficient. And finally, 58c1 has to equal 3, that coefficient. Pretty close to being done. I have that c1 is equal to 3 over 58. I don't really need to plug that back into the equation I had on the previous page. This is good enough. I had that written in terms of c1, c2, and c3, and now I know what c1 is. This tells me that c2 is equal to negative 3 over 58. Done with that one. And finally, I can solve this one for c3. So we have 14 times 3 over 58 minus 7 times 3 over 58 for my c2. I'll bring the 1 over there, minus 1 equals c3, this whole thing divided by negative 3. This is just a little bit of algebra, a little bit of math fiddling around, but we could get a coefficient. And that's it. I'm done. So actually we did all three steps. Now, there is a bit of a shortcut approach to this. So I described that a minute ago as being sort of a brute force method. Well, there's another way to do it that isn't so brute force, and I'll just cover it rather briefly here. So let's say we had that g of s. So to attack this, I go c1 over s plus 2. I do the breakup business. And I write out my answer. c1 e to the negative 2t plus c2 e to the negative 5t times the unit step. Again, just a little reminder. Now, I could recombine these two and get a common denominator and do what we did in the previous slide. Or I can use, sometimes it's called the cover-up method, which is kind of a funny term, but what you do is you take g of s. Actually, let me be more specific. Let's say I'm going after c1. c1 is equal to s plus 2 times g of s evaluated at s equal negative 2. Now this only works for roots that have multiplicity 1. What this is doing is it's canceling out that s plus 2. So if I do this operation, what I'm left with is s minus 4 over s plus 5. And then I let s equal negative 2. The negative 2 comes from that root. Oops, that root. So what this gives me is, let's see, negative 2 and a negative 4, so negative 6 over 3. or negative 2. Great, so C1 is equal to negative 2. Boom, done. C2 is equal to s plus 5 times g of s, evaluated at s equal negative 5. And what that provides is s minus 4 over s plus 2 at s equal negative 5. And that is negative 9 over, let's see, s equal negative 5, so over negative 3. So it looks like C2 is equal to 3. We can check that. If we put C1 equal negative 2 in here and C2 equal 3 into that and get a common denominator, so I'll just hog out a little bit of space like so for a check. So we have negative 2 over s plus 2 plus 3 over s plus 5. If I do the common denominator, I'll get a negative 2s minus 10 plus 3s plus 6. So I get s minus 4. Boom, that checks with that. So this is right. And it's a quick way to figure out the coefficients of simple real roots. So one approach you can take is you go after your simple real roots using this method, this cover-up method, this way of canceling out terms in the denominator and quickly getting coefficients. Plug those back into your expansion when you break up the function, and then go ahead and use that brute force method where you get a common denominator and solve for the remaining coefficients. That's it. So a introduction, a review, depending on your place in all of this, of inverse Laplace transforms and partial fraction expansion. Again, my name is Gordon Parker from Michigan Tech, and thanks for watching.